Okay, so where we left off last time was we're talking about nitrations, right? And we said that you have benzene, and you treat it with nitric acid and sulfuric acid. You're going to put a nitro group on the ring. We said the reason that nitrobenzene is so important is it's our bridge from benzene to aniline. Right? And we get there by doing a reduction. Right? And we said there are basically two ways to do it. There's taking a metal like iron and adding HCl, or tin and adding HCl, or zinc. So all of these, and HCl. So all of these will take your nitro compound to the aniline, and then the other way to do it is H2 palladium on carbon. Right, so those were the ways you get from nitros to anilines. And I use this word reduction, right? And I want to take a second to define oxidation and reduction in an organic context, because the way we think about it in organic is different than the way you thought about it in Gen Chem, right? And we're going to do oxidations and reductions a lot going forward, so I just want to kind of get us all on the same page. All right, so in Gen Chem, you were given some probably mnemonic device to help you remember it. There's one about like a lion or something. What's the lion one? Leo the lion says "grr." I said something similar to that, and everyone looked at me like I was dumb in the first class. And I was like, no, I think that's it. The one I had was oil rig, right? That oxidation is loss of electrons, and reduction is gain of electrons. And this works for organic compounds, but the problem is that when we draw a carbon or another atom in an organic molecule, we never write beside it, oh, +1, +4, right? Where in organic at the times, or in Gen Chem, right, there's a lot of times you wrote like, oh, this is the +2 version of this ion or whatever. We don't do that in organic. So we kind of track the oxidation or reduction of our molecules and atoms a little differently in organic. So in organic chem, so reduction is when you add atom hydrogen bonds or the loss of atom oxygen bonds, right? So you either increase the number of hydrogens that are bonded to your atom, or you decrease the number of oxygens bonded to your atom. Oxidation is the exact opposite. Right, so Oxidation is you lose hydrogens off an atom and you replace them with oxygens. For both of these, I'm going to point out that halides count as oxygens. So I can replace oxygen with halide, right? So oxidation is adding more atom halogen bonds. Reduction is removing atom halogen bonds. So halogens and oxygens kind of work interchangeably here. So for the thing that we already know, right? So let's look at our nitrobenzene. So we look at our nitrogen here. How many oxygen bonds are there in nitrobenzene to the nitrogen? I'm going to say 3. There are 3 bonds between a nitrogen and an oxygen, right? 1, 2, 3. And there are 0 NH bonds. Right? So now when we go to aniline, right, we have 0 NO bonds, and we have 2 NH bonds. Right? So we decreased the number of nitrogen-oxygen bonds. We increased the number of nitrogen-hydrogen bonds. This nitrogen from one side to the other is reduced, right? We reduced the number of oxygen bonds it had. So that nitrogen is reduced. Right, so we can do this with any atom. Most of the time we do it with carbon, the occasional nitrogen. Anytime I show you a reaction that you don't know, it's just magic. In about a month, you're going to know this reaction, no problem. You'll be like, oh, this is easy, Wakefield. But right now, it's just... All right. So if we look at this carbon here, how many oxygen bonds does it have? 1. So I have 1 CO bond, and I have 2 CH bonds, right? Now in the product, how many CO bonds do I have? 3. And I have 0 CH bonds. Right, that carbon no longer has any hydrogens on it. Right, let me make it green. So this carbon got oxidized, right? It got oxygens. So on some level, right, you are kind of doing the same thing that you did in Gen Chem, where you're like tracking how many electrons are around that carbon. Right? We can figure out their oxidation states, but we really don't have to. All we have to do is count how many hydrogens and oxygens are bonded to our atom and figure out if the product has more or less. Did you know how any of these reactions work? It doesn't matter. It doesn't matter how the reactions work, right? My green carbon up top, did it get oxidized or did it get reduced? Did it gain oxygens or halogen bonds, or did it lose oxygens or halogen bonds? It lost them, so we reduced the number of oxygen halogen bonds, or sorry, atom halogen bonds or atom oxygen bonds we have. So we reduced that number, so my green carbon here got reduced. So for this next reaction, how many carbon oxygen bonds do we have? 2, right? 1, 2. And then in the product, we have 1 carbon oxygen bond, right? We can also count our hydrogen bonds. We have 0 CH bonds. And then over here, we have 1 CH bond. So again, we reduced the number of oxygens on our carbon. So this was reduced again. Seem reasonable? So whenever we say something's oxidized, you're adding more oxygen or halogen bonds to that atom. Whenever you say something is reduced, you're removing those oxygen and halogen bonds and replacing them with hydrogens. The only thing here is to point out is removing H plus from an atom is not doing an oxidation, or is not an oxidation, let's say. Right, so just deprotonation. Right, so we say that you lose carbon-hydrogen bonds, and that's an oxidation. But just saying, hey, I'm going to treat my molecule with a base, to make a negative charge, doesn't do an oxidation. Right, losing H plus doesn't change the oxidation state of your carbon. So oxidation and reduction remove or add hydrides. So they remove or add H minus from the atom, effectively. It's adding H minuses or taking H minuses away. Taking off an H plus doesn't change the oxidation state of your carbon. Now that we've had that little aside, back to our regularly scheduled reaction programming. So next up is sulfonation of benzene. All right, so here you add SO3 and H2SO4. That's going to add a sulfonic acid. To your benzene. This gets abbreviated, right? You don't have to draw out the whole functional group, kind of like on a nitro group. You don't have to draw out the whole structure. You can just write NO2. Here, this can get abbreviated to, we have space, SO3H. So the mechanism here is pretty straightforward. Right, we've got to make our electrophile. So this is the structure of SO3. We've got our sulfuric acid. And one of our lone pairs on an oxygen will grab a proton from sulfuric acid. Make a positive oxygen there. We make our sulfate. That's our electrophile. That's what our benzene is going to react with. So your benzene, there you go, then reacts with this. Just like we've seen before, you're going to add to the atom beside the positive atom and push electrons over. Give everyone a beat here, because I'm not going to get the last structure on this, I don't think. Maybe I will. And then we're going to lose our proton. There you go. We'll make it so you can actually read it. And that will give you your product. Fair enough? Next up is how we add carbons to aromatic rings, and that is the Friedel-Crafts reaction. All right. So this is how we add carbons. So what you need here, so you need an alkyl halide plus a catalyst to make this reaction work. Your alkyl halide needs to be either secondary or tertiary. Primaries don't work. So the mechanism here, you should be kind of thinking, secondary, tertiary halides, primaries don't work. Maybe we go through a carbocation, right? Because we're allowed to make secondary and tertiary carbocations. We aren't allowed to make primary carbocations. So let's look at some examples here. So you have your alkyl halide, right? And you need a catalyst. Thankfully, we get to use the same catalyst that we used for the halogenation of benzene. So for chlorides, you can use FeCl3 or AlCl3, either one. and you'll add your alkyl group. So basically, you're removing the halide and just putting the benzene in its place, right? So I always like to point out you want to connect the dots, right? The carbon on the aromatic ring, you draw a bond from the carbon that had the halogen to that carbon, right? So you should always be connecting two dots. I've had people on exams like just take it and like smush the two carbons together into one. I get up with a thing with like 5 bonds on it. Ugh, bad, right? So you always need to make sure that you have a bond that's going to connect your two dots, connect your carbon from your aromatic ring to the carbon that had the halogen. Right? For bromine, same thing, you use FeBr3. Just like when we did the halogenation, make sure you match your halogens, right? You want to make sure that you have, that if you're using a chloride, that you use a catalyst with a chloride on it. If you're doing a bromide, make sure you use the catalyst that has the bromide on it. So let's talk mechanism. We're going to do the top reaction. The mechanisms are the same for catalyst and halide, doesn't matter what they are. Right, so we've got our benzene. So the mechanism, you have your alkyl halide, you have your metal, you add to the aluminum, right? So this is very similar to when we did the halogenation. The thing that changes here is before the benzene has a chance to react with this complex, the chlorine goes, I've made a terrible mistake. I want to have my electrons back, right? So what happens is the carbon chlorine bond will break. So the chlorine will get electrons back, right? It'll get the electrons back that it shared. And you'll end up making a carbocation plus your aluminum complex. This carbocation is your electrophile. This is the thing that adds to, or the benzene adds to. So then we can just put this in our general mechanism like we've seen before, right? So you can have your benzene, going to add to the carbocation, right? And then we can use our aluminum AlC and use it as a base to remove that hydrogen that makes our benzene ring plus HAlCl4, and that falls apart into HCl and AlCl3. So in simple cases, this is pretty straightforward, right? We just have to identify the carbon that has our halogen, identify the carbon that has, and identify the carbon on the benzene that we're going to put make the bond to, and you just get your product, right? Connect the dots. So right? You're just like, all right, I'm going to remove my halogen, put my aromatic ring in its place. Connect your dots, right? Same thing down here, just remove the halogen, put the aromatic ring in its place. But because these mechanisms go through a carbocation, right? Whenever you have a carbocation, there's a chance that you could have a rearrangement, right? So you always have to look to see if the carbocation you're generating can rearrange before the reaction happens. So, like for example, all right, I have a secondary halogen, so that means I'm going to end up making a secondary carbocation, right? And I have to say, okay, can I rearrange that carbocation? Can I move a methyl group or a hydrogen to make a more stable carbocation? In this case, I can move a hydrogen. Right, so I go from a secondary carbocation to a tertiary, that's more stable. Now my benzene ring is going to add to the tertiary carbocation. And I'll make that, right? So you just have to be mindful of rearrangements when you're doing these, right? Because they always generate a carbocation. It doesn't matter how you got to your carbocation. What matters is once you get there, to check to see if it can rearrange. All right, same deal. I have my halide. I make the carbocation. All right, what's nice is the initial carbocation is always where the halide was. Then you have to think, okay, now can I rearrange this? I have a carbocation beside a small ring, so I can do a ring expansion. So if you remember, 1, 2, 3, 4, 5, your electrons can come over, right? You break the bond between carbon 1 and carbon 4. You make a new bond between 4 and 5. Right? Electrons left carbon 1, right? We broke the bond between carbon 1 and carbon 4. Those electrons went to make a bond between 4 and 5. That means carbon 1 gets a positive charge. And then your benzene adds to this. And you get your product. So it's always going to do the rearrangement first before your ring tries to add. So speaking of rearrangements, if you try to use a primary halide, you're never going to get the product from the addition of the primary halide, right? So, because it's always rearranged. So let's say you have this, right? You're never going to make this product. right? You don't get that product. What happens instead is you have your chlorine, your aluminum bonds to it, just like you would expect, right? Now the aluminum is really tugging on that chlorine and it's trying to break the carbon-chlorine bond. But that bond can't break because it's going to make a primary carbocation. So what happens is that bond doesn't get to break until the hydrogen one atom over kind of helps push that chlorine off. And what happens then is you generate a secondary carbocation. So you never make the primary carbocation. My form. You never make the primary carbocation, so you can't ever end up with this product, right? You wanted butyl benzene, but instead you ended up with sec-butyl benzene, right? Because you didn't ever get to make that primary carbocation. So if you use a primary halide, it's always going to rearrange to make at least a secondary carbocation. And as a general rule, it's going to be faster if you want to make sec-butyl benzene to just use like 2-chloro butane, right? So then you don't have to like worry about a rearrangement or anything happening that might be slow. You just get to make the product that you exactly want, no problem. So we can't use primaries because they always do something a little wacky. Then there's methyls, and methyl halides actually work really well, right? But they go through a different mechanism. So right? Because we definitely can't make a methyl carbocation, right? Those are even worse than primaries. But if you have benzene, and you add like methyl chloride and say FeCl3, you'll make toluene. Right? But we're not going through a carbocation, so how does this work? The mechanism is very similar to a halogenation, right, with bromine or chlorine that we had learned before. So you have your halide, and same thing that we've seen, right? Our halide's going to add to our metal. Right. And now this, if you like looked back in your notes, this looks almost exactly like the structure we had for bromination, right? Where instead of there being a halide on the end, you have this methyl group, right? And it's going to act, though, the exact same way that the metal complex that we used in the mechanism for bromination works, right? So we're not going to break the carbon chloride bond and make a carbocation. Instead, this is our electrophile. Our benzene is going to add to this complex and break that bond for us. So I'm going to have to go over a slide, sorry. So I have our benzene here. We have our methyl, Cl, Fe, right? Our aromatic ring adds to the methyl group and pushes the electrons onto the chlorine. So since the methyl is small, it's easy to kind of do what almost amounts to like an SN2-like reaction to it. Right? You attack the carbon, you break that bond, and then we just fall back into our nice, normal, happy, safe mechanism. Right? Use our iron complex as a base. We get toluene, and we get FeCl4. So the mechanism's a little different. We don't go through a cation, but end result is we end up with a carbon on our chain. So far, so good? Okay. Now, let's go back to butylbenzene. Right? Let's say we really want to make butylbenzene. Let's say, I don't know, this is the cure for COVID right here, butylbenzene. And Joe Biden looks out at the world and goes like, sophomore organic students, these are the best people to make this compound for us. You're our last hope. Right? He's like, how are you going to do this? And you're like, well, crap. All Wakefield's told me so far is I can't do it. But the world's counting on me. I've got to come up with something. Don't worry. Friedel and Crafts, they have your back. Right? There's a variation on the Friedel-Crafts reaction called the Friedel-Crafts acylation. Right? The electrophile that you make has no carbocation in it, so you don't have to worry about any rearrangements. So it'll let you put long chains on your benzene ring, but you have to do a little bit of extra work. So the Friedel-Crafts acylation, you take an acid chloride, so you replace the OH of an acid with a Cl, right? That's an acid chloride. And then you use a catalyst. And again, we get to use the same catalyst we used for chlorination. So you can use aluminum trichloride or iron trichloride, right? And what happens is you just remove the chlorine and you put the benzene ring in its place, right? No rearrangements, nothing you have to worry about. This is a simple erase the chlorine, put the benzene in its place, right? Now, I want to point out, I said acid chloride specifically. No acid bromides. This only works with chlorines, right? I'm sure if I dug deep enough, I could find an acid bromide in the literature, but I can't think of one I've ever seen. So they're really not a thing. So we can just use acid chlorides. So how does this work? What is our mechanism? Oops, nope. Try again. Try again. So what is our mechanism? All right, so it's slightly different than the alkylation, but not much. So the beginnings are the same. Like you've only drawn this step like a million times now. It should be ingrained in your brain. You're like, oh, metal with 3 halogens around it. A halogen, got to make a bond to it. All right. Now, instead of making a carbocation, what ends up happening is the lone pair on this oxygen will push down and push out the chloride and make an oxonium ion. And then this is our electrophile. So that's what's going to react with the benzene. So we have our chlorine add to our iron. We use the lone pair on our oxygen to push down and make an oxygen-carbon triple bond. Oxygen gets a positive charge. That's our electrophile. So now, again, we run right into our general mechanism. We add to that carbon. We push electrons back up to the oxygen. So again, we're adding to the atom beside the positive atom to give the positive atom back its electrons. And again, we get our same HFeCl4, which falls apart to HCl and FeCl3. Right? So now we can put like kind of straight chains onto our benzene rings, but there's an oxygen in the way. You know, and Biden's like, this is a bunch of malarkey. I need butylbenzene. I don't need this ketone on here. And you're very impressed with Biden's like chemistry knowledge. Like, wow, way to go, Joe. Right? But what we can do is we're able to remove the ketone from the carbon chain and just get to a straight chain. So we can say, all right, we can add an acid chloride. And we can make our ketone, right? Now I've got this straight chain, but I have a ketone where I don't want one. So just like we did with nitro groups and turning them into anilines, we can do the same thing here by turning ketones into CH2s. So we can remove that ketone and get a CH2. You'd be like, get off my back, Biden. Look at this. There's your butylbenzene. Right? So how can we do this? There are two ways to do this. The first is H2 and palladium on carbon, tried and true. Right? It's going to remove our ketone, make it a CH2. The other way to do this is zinc, mercury amalgam, and HCl. Right? This is probably a little less good for you because you're just taking a paste of zinc and mercury and adding acid to it. What could possibly go wrong playing with mercury paste? I don't know. This has another name. This is a Clemenson reduction. We don't usually make reactions like this anymore because I think students have these things that are called rights now. We're not allowed to just like give them poisonous chemicals and be like, hey, it'll work out. Like, yeah, you're replaceable. If you're here in 3 years, that's a bonus. Here's some mercury. See what happens. Right? So what you should think whenever you see a CH2 at the benzylic position of an aromatic ring, so if you see a CH2, you should think, well, at some point, this was a ketone, right? Because you have no way to put a CH2 directly onto an aromatic ring. You almost always have to go through a ketone first. All right, so whenever you see a CH2, think that was a ketone, and then work from there. Like, okay, I have to make a ketone at some point and then reduce it. All right, so when you see a CH2, you should think, all right, that CH2 had to be in a previous life, it had to be a ketone, right? So you know if you see a CH2, it was a ketone beforehand, right? So how can you turn the ketone in B into the CH2 in our given product? Clemmensen, so we can like zinc, mercury, HCl, like, my 80s are overrated. Let's play with some mercury. This is where I point out that organic chemists have the shortest lifespans of all chemists. Because we're like, it gets me to 85% yield, but it might kill me. I'll wear 2 gloves. It's fine. How can I turn my benzene ring into this ketone? What do I need to do? When you look at it, you need to say, okay, I'm adding this whole piece. So I'm just replacing the aromatic ring on that piece with a chlorine. So you just have to redraw that piece and slap a chlorine on it. Right? And then you have to add your catalyst. And you get your product. Right? So just always be mindful. When there's a CH2, it was probably a ketone somewhere else in your synthesis. Right? Because if you tried to just do this, you wouldn't add the CH2, it would rearrange, and you would make the tert butyl one, right? You'd end up rearranging that and making a more stable carbocation. Right, so you'd get like, and then the hydrogen would hop over. I should probably put a plus and a minus here, push electrons there. It would give you the tertiary carbocation as you would add to. So this is pretty much the end of new reactions for a while. So going forward for the next like couple days, at least one day, maybe part of a second, is we're just going to go over a bunch of rules on if you have one group on your benzene, where does the second group go? Right? When you have 2 groups on your benzene, where does the third group go? But we're going to be using these like 7 reactions that you just learned. So for a couple of days, there's going to be no new mechanisms. So with that, I will see you guys on Monday.